Dimension, let's add on rank and nullity. So let's start by talking about a set of basis vectors. Suppose B1 through BP is a basis for a subspace. The coordinates of x relative to the basis B are the weights, so that you can write x as a linear combination of those B vectors. So sometimes they say x and then they put it in square brackets, and then they put a little subscript of B. So that's called a coordinate vector of x relative to the basis vectors B. I was thinking about coming up with an example, and can't really think of one. Oh yeah, I thought of one. Let's think about the easiest to visualize is to go back in 2 dimensions and try to see how this thing might look like in 2 dimensions, or what this might mean in 2 dimensions. So let's imagine you're in 2 dimensions, you're playing a video game. I don't know if video games are a good thing to play. So we have our regular basis vectors for 2 dimensions, right? The I, J vectors. And then let's say you're in a spaceship in 2 dimensions, you're flying on this curve, and then you're going to create a new set of basis vectors. Let's say we're in point 1, here. And let's say at this point 1, you're establishing a set of new basis vectors from that point. Okay. And so let's say this is the vector, let's call this B1 is equal to the vector 1, -1. And then your B2 vector is 1, 1. Yeah. No. Yeah, this is just an example. I mean, I was going to purposely not make it perpendicular, but now that you caught that, I'm going to purposely make it not perpendicular. So let's say your vector B2 is, let's call it 2, 1. So it's not perpendicular. There's something about perpendicular basis vectors, and that's an ideal situation for us. But it's not necessarily the case that that's going to happen. And so we're going to go through a process near the end of the semester called orthogonalization, where we're going to have one basis vectors, and then we have a new set of basis vectors, and then we're going to force our new set of vectors to be perpendicular and unit length, which makes it nice and easy to work with. Yeah. Well, we can always move those vectors back to the origin if we need to, and we will think about it that way. So our old basis vectors is the ij, and then we have a new set of basis vectors which like Brian was asking about, we're probably going to want to be interested in moving it back to the origin so that we can see it a little bit neater. So in fact, let's draw it here in the origin now. B1 and B2. So now you're here in this, you can think about being in your spacecraft flying around and then you see something off to the side. Um, in say you see an object over here that you're interested in looking at, and in the original basis vectors where we have the I and J, this is a basis 1, 3 or something. This is a point 1, 3. And so what you want to do is you want to express 1, 3. You can think about it as a point, you can think about it as a vector, but you want to express 1, 3 as a linear combination of these two vectors. And that's going to be the key, is that when you're in your spaceship, what you want to do is you want to use your basis vectors to go around and scan the area. So what this notation is saying is that your x point, you can think about it as a point or you can think about it as a vector, is your vector 1, 3, right? And that would be how we would denote our x vector. But we might be interested in using the new basis vectors. So let's say B, our basis vectors B1 and B2. Are these two vectors, and I want to express this point 1, 3 in terms of B1 and B2. So now I have to find weights. So I have to find weights C1 and C2, so that if I have these two vectors, 1, -1, and 3, 1, I have to find weights C1 and C2 so that, say it again? 2, 1, yeah, thank you. I have to find weights C1 and C2 so that this is going to be the case. Now, can we do that quickly? I don't think we can do that by inspection. Can we? 3, no. So we have to solve for this. Or you can just pull out from alpha, right? No. I should make a test where you don't need calculators. That means it's going to be a lot more theoretical. But that's what linear algebra is. It's theoretical. Yeah, I've given exams where it's like a 2-day exam where a 2-day exam. One day is all calculators, and then another day would be no calculators. All right, where was I? I was pulling out Wolfram alpha. What is it? Okay. Agree? All right. So I don't have to do this? C1 equals -5/3, and C2 equals what? Positive. All right, so those are numbers that we have. And so what this says is that our x vector can now be written, instead of 1, 3, can now be written with respect to the basis. And this would be minus 5 over 3 and positive 4 over 3. So if you're flying in your spaceship, instead of setting your spaceship coordinate to 1, 3, which wouldn't make sense because that's like the absolute coordinate system, from your spaceship's point of view, and you have to add where your point is now, so you're at a certain point. From the point, you would go negative 5/3, positive 4/3, and then that's where you're going to be able to view that point relative to your spaceship. Yeah.
So is it okay to think about it as you're essentially making your ship?
Yeah, you're kind of making your ship the new origin, if you remember to do the offset to where your ship actually is. The basis that you're creating, yeah, you're eventually going to want it orthogonal, because the calculations for orthogonal vectors are so much easier than something like this, where you have one basis is 1, -1, another basis is 2, 1. The calculations for that, for certain things that you want to do, might not work out very quickly versus something that is orthogonal. But that making your basis orthogonal is a later subject, so won't worry about that right now. Okay, so this would be a reason why you would want a different basis and then express your point with respect to that new basis, new set of basis vectors. Still a vector, yeah. So this is a vector, but negative 5/3, 4/3 it doesn't make too much sense with respect to the original coordinate, but from your spaceship's point of view, then that does make sense. I don't know if I answered your question. Yeah. Yeah. So if you're actually programming this game, then you're going to need to keep that in mind. Okay. All right. So that's the idea behind a new coordinate system and basis vectors for coordinate system. Now let's go back to the idea of our row and column spaces, our subspaces, and count the dimensions. So let's define dimension first. Dimension of a non-zero subspace, denoted by dim h, is a number of linearly independent vectors that span that space. In other words, a number of vectors in the basis that you have. So remember what a basis is. A basis is a set of linearly independent vectors that span a space. And so when we say basis, we want to make sure that 1, they're linearly independent, and 2, they span the space that you're talking about. So the dimension of our special degenerate case, the zero vector subspace, is 0. You can think about zero vector as a vector, but it's not really a vector, it's just the point. So we'll call that dimension 0. And then you're not talking about the whole space. Yeah. No, you're not talking about the whole space. Yeah, you're just talking about the whole space, the whole subspace. Wait. So in R2, remember there's 3 possible spaces. The 0 vector space, that's a degenerate space, that has dimension 0. The whole space, the whole 2-dimensional space, which is going to be spanned by 2 linearly independent vectors, or a line passing through the origin, which is a 1-dimensional vector space, subspace. and that's only spanned by one vector. So we've been talking about the number of vectors that span something, and that's exactly what the dimension is. The dimension is the number of vectors that span, the number of linearly independent vectors that span the space that you're talking about. All right, so the dimension is a number. A subspace is a space that you can define or describe by a set of vectors. Okay, so when we talk about the dimension, you're talking about just the number, not the whole space. So, two definitions here describe the dimension of something. The rank is a dimension of the column space, and the nullity, which again, this is not covered in the book. The word nullity is not in the book, but it's in every other linear algebra book. The nullity is the dimension of the null space. And I also want to include for that first one, the rank, also again, the book does not define row space in this section. It actually looks at row space later on in the textbook, but it's the same dimension as the column space. As we saw in the previous class, it may not necessarily live in the same vector space, but the dimension will be the same. What? You can, but I'm not going to. So in this example that we had a 4 by 5 matrix. The column space, they were vectors. The column space was a set of vectors in R4, and we had dimension 3. The row space were vectors in R5, and we still had column 3. Okay, you can think about the row echelon form. When you reduce into row echelon form, you can count the number of pivot columns and the number of non-zero rows are going to be the same. That's the rank. So in this case, the rank is 3. The nullity is the dimension of the null space, and in this example, the rank is 2. Yeah. It doesn't matter. You can reduce it all the way if you want, but all we care about is the number of pivot columns. Depends on the size of your matrix. Yeah. You still can. It doesn't matter. Yeah. Yeah, if you reduce it, it still would be fine. It's because it's row equivalent, so anything that you do would still be okay. Huh? For the nullity, the rank for the null space is 2 because there's 2 vectors that span the null space. So I'm not gonna copy the whole thing. I'm just gonna say, recall to use this as our example. Example from last time. So we have 1, 2, 3 pivot columns. This is the null. This is not. I'm sorry. This is not the nullity. So rank equals 3. Also, in this form, the nullity is 2. So in this form, also, we got the number of non-zero rows equals 3, and that's also the rank. Okay. The nullity if you remember, if you reduce this, this is counting the number of free variables. We got 2 free variables, so that the nullity equals 2. And that's a dimension of the null space. And the number of free variables you have tells you how many vectors span the null space. Okay? All right. So we're ready for the big theorem here. The rank and the nullity add up to what? The number of columns. 1, 2, 3, 4, 5. Not the rows, the number of columns. So that's going to lead us to our what we call the rank theorem. The rank theorem tells us that the rank and the nullity all equal to the number of columns. And the non-pivots are the free variables, which is the number of, yeah. So if you just look at these green and red arrows here, they amount to every single column that we're talking about. So we got 3 pivots, and then if you don't have a pivot, then you must have a free variable. And so they would just add up to the number of columns. That's not a proof. You can look at the book for the proof, or you can just search proof of rank theorem on the internet, and I'm sure you'll find something interesting. Hell, you might even find me a couple of classes ago proving it. Yes. If all of them are linearly independent, then you'll and the number of rows equal the number of rows, number of columns and stuff like that. If you have a square matrix and they're all linearly independent, then your rank is 0. I mean your nullity is 0, which is, and your rank would be the whole thing. Had to add up. Yeah, the number of rows. Yeah. Oh, sorry, the number of columns. The number of columns add up to the rank and the nullity.
Even in this example, the number of rows in this matrix what dimension one generally.
Yeah.
Over 4 dimensions.
For the column space, you're in 4 dimensions.
How you could have like a rank of 3, so you essentially have vectors that cover all of the 3-dimensional space within that 4-dimensional space. And then the nullity is the space that can't be reached by those 3 independent vectors, which is a 2-dimensional space, so it's like a plane. So I'm trying to visualize it.
So don't visualize it because you're in 4 and 5 dimensions. The other thing is that well, if we break it down to 2 or 3 dimensions, then your rank is either a line or a plane, or the whole space. And then your nullity would be If your rank was a plane, then your nullity would be a line in 3 dimensions. And if your rank was a line, then your nullity is a plane. Yeah, so no. Right, you're not going to be able to visualize it. You can certainly imagine it. All right. Rank, nullity, column space, row space, null space, and what else? The basis theorem. What's the basis theorem say? So if you have a p-dimensional subspace of Rn and any linear independent set of p elements in H is automatically a basis. Also, any set of p elements of H that spans H is also automatically a basis. So we kind of did this in our simple example in the first page over here. We have the I, J vectors in R2. And then we switch basis to B1 and B2. I'm sure there's some effort. So this says that if you have 2 linearly independent, you're in R2, and my subspace spans all of R2 in this case. If you have any 2 linearly independent vectors, then that's going to be, you can set that as your new basis. Also, if these 2 span everything, then that can also be a basis, because if they span something, and then there's only p elements, and that's exactly the dimension, then it would span everything. Then it would work as a basis, because remember that a basis, 2 things, they have to be linearly independent, and they have to span whatever it is you're talking about. So this is almost saying what the definition was saying. Okay? All right. Remember the invertible matrix theorem? There's like A through J, K. Well, now that we know about rank and nullity, we can add more to that. We're not doing determinants yet. Again, we're not talking about determinants yet. That'll be in a couple of minutes, actually. So A through L was all the stuff that we talked about. So now we can add on a few more things to determine if a matrix is invertible. So now that we've talked about column space, row space, null space, we can also include columns. Whenever we see column here, we can also say row space. So the columns of A form a basis for Rn. We have to start off saying that this is an n by n matrix. So for it to be invertible, it has to be a square matrix, right? First. So we have an n by n matrix. So the columns form a basis for Rn. And because this book is not talking about row space, it didn't mention rows, but you can also replace that with rows. So the rows themselves n of them will also form a basis for Rn. Well, so I don't know why they put dimension column A and rank A, because they mean the same thing. That's by definition, but that's what they did. So dimension of the column space equals dimension of the row space, and that's equal to n, the number of rows or the number of columns. And dimension of row, which equals the dimension of column, is actually the rank. And then the nullity, or the null space, is just a zero vector. And when your null space is just a zero vector, then the null space has dimension 0, or the nullity is 0. By the way, this 0 here is a 0 vector. How does it go? Arrow? No. R arrow? No. I don't know. Trying to do, it's a LaTeX command for an arrow. Harpoon. You have to spell it out. Is it right arrow? Oh, wait. I want the arrow on top. Vec? Oh, vec. That's right. Vec. There you go. So the 0 vector, if your nullity is just a 0 vector, which we've seen, right? That means row reduced. It's just going to be perfectly staircased and no free variables for an n by n matrix. Then your nullity is 0, which means 0 is the only vector that gets sent to 0. Anyways, if all these are true, then your matrix is invertible. You can find the inverse for your matrix. Okay? So this just adds on to it. And when we get to determinants, then we'll also add that one more piece of information. Any questions? Okay, so all these we've already gone over, we've already seen. So this is the focus. All right, I think we're done with this section. I thought I was going to do a problem or something. I want to do that one. All right, let's do 13 or 14, talking about basis and stuff. 13? Ooh, this thing is long. All right, 13, find a basis for the subspace spanned by the given vectors. So we want to know, this is an R4, right? These are 4 vectors, and there's 4 of them. So if these are all linearly independent, then you can say this whole thing spans all of R4. But we don't know that, so we need to check if they're linearly independent, and we can just put it in a matrix and then row reduce. So that's what we're going to do. That's what Mathematica is going to do. 1 minus 3, 2, negative 4, minus 3, 9, negative 1, 5, 2 minus 6, 4, negative 3, 4, 12, 2, 7. And let me pull out Wolfram. All right, let's examine this matrix that we got, the row reduced, and this is reduced row echelon form. So we take a look at the pivot columns. There's 3 pivot columns, right? So it looks like this matrix here is linearly dependent from the rest of them with respect to the rest of them. It looks like it's linearly dependent on the first one, if you look at it that way, right? But the other 3 are independent. So we can say that these 3 vectors, if we call this vector v1, v2, and v3, so v1, v2, and v3 form a basis for the subspace. And then we can apply all the other stuff that we've been just talking about. So this is the column space of A, if we call this A. The row space would be these rows. So 1 minus 3, 0, 0, 0, 0, 1, 0, and 0, 0. Oops, yeah, it doesn't matter. No, I was right. Because you have to look at it row-wise. I was kind of getting mixed up with the row and the column. No, I could have taken it from, as long as I'm taking the first 3 rows here, I could have taken these first 3 rows. Or what? Yeah, either one of those. So this set of vectors here is going to be basis for the row space. This is row of A. I guess they use capital. And then one more piece of information. So we're looking at this matrix A, the nullity. What's the nullity? Nullity is 1, so your null space is a one-dimensional subspace, and you got a free variable here in x2. So the null space will be spanned by one vector, and if we figure out what that one vector is, then we can say what it's spanned. Whatever it is I'm trying to say. Okay? Does that make sense? No. Column space and row spaces are different. They will span different things, and especially apparent if the dimensions are different.
I understand that, but the first example, when we were first looking at the columns, I think we were first, yeah, we were first looking at the columns, you have B1, B2, B3, state that it forms a basis for the subspace. You have to refer to, that is not column space, even though we were looking.
Oh, this is the column space. It's not the row space.
Right. I guess, yeah, so where you have written subspace there for that example, that's interchangeable with column space.
I guess it would be clearer if we put col A here. That's what that subspace is. Yeah. When I say subspace, I meant column space, but when you say subspace, you can also easily mean row space or null space. So you should be clear when you say subspace. And I wasn't. So column space. They're not that interchangeable. Row space and column space are both subspaces. And for square matrix, they're both subspaces of the same Rn, whatever the n is. But if it's not a square matrix, then one's a subspace of Rm and the other one's a subspace of Rn. But the null space and row space are not only that, but they're subspaces of the same vector space. The row space and the null space live in the same vector space. Okay? In the row space and the column space, no, row space and the null space. Because the row space and column space might not live in the same space. They can't be, the mutually exclusive thing. But the row space and the null space are mutually exclusive. That means they can't have anything in common except for 0, the 0 vector. Oh, I may have said that, huh? It's the row space and the null space. Because the row space and the column space have the same dimension. So if they're in R3 and then the dimension is 2, then, I guess it's still, that's not a good example. A good example of where that would fail would be if it's not a square matrix. All right, I think we're done with chapter 2. So we skipped a bunch in chapter 2. Can't remember what, but yeah, because I can't remember. We did. So you should keep track of what chapter 2 stuff we did. I know we did 2.8 to 2.9. That's the last thing we did, and then 2.1 and 2.2. We might have done 5. We did 2.5, the LU factorization, and then we skipped everything else. We skipped partitions. Yeah. Leon, that's economics. And then we skipped the computer graphics applications. That would have been fun, but we need to move on. All right. We're done with this. We're on to chapter 3. Guess what chapter 3 is? Determinants. Yay. So let's start with something nice and comfortable, and that's determinant of 2 by 2 matrix. And we saw this defined earlier when we were talking about inverses, a special shortcut for finding the inverse of a matrix. So determinant of a 2 by 2 matrix is the product of the diagonals. That's the A11 and A22 minus the product of the other elements, which we call the wings. I don't know why we call it the wings, but it's called the wings. So A21, A12, and that's our determinant. So the determinant gives some sort of numerical, not numerical, but scalar, to be more precise, a scalar measurement of, measurement is in quotes, scalar measurement of a matrix. So what we want to do is this works, determinant, idea of a determinant works for square matrices. So what we want to do is extend this to a 3 by 3 and a 4 by 4 and etc. And so the way that's going to be defined, well, they do an interesting activity in the book that I think is kind of interesting and neat, but tedious. So I'm not going to do it, but I'll point it out. Oh, I didn't even show it here. Let me just paste this information here and skip down a little bit. So the determinant of a 3 by 3 matrix is going to be given by some sort of expansion where we expand. We say we expand on in this example, we expand on the row. So we're looking at all the elements in the first row. And then after you take the elements in the first row, you take the determinant of the submatrix that's left. So if you expand on the first element in the first row, A11, you cross out the row and the column that it's in, and then what's left over here is A22, A23, A32, A33, and then you create a submatrix of that. And then you take the determinant of this. And then you expand, and there's this mystery negative sign over here. Well, yeah, if it's 0, then the rank is n and stuff like that. But yeah, we'll get to that. This is like the cross product. If you remember the cross product from Calc 3, the way you compute the cross product is you're essentially finding the determinant of a 3 by 3 matrix where the first row happens to be the ijk vectors. Really just meant for computation's sake, and there's not any deep mathematics going on there. It just happened that the cross product works for that, or the determinant. So there's this expansion on a particular row, in this case the first row. We'll see in a couple of theorems later that you can expand on any row you want to get the matrix. And I encourage you to take a look at the textbook and see how they came up with the formula for the determinant of a 3 by 3 matrix, because what they did is they tried to row reduce it, and then they want to make sure that all the diagonal elements are not equal to 0. And then when they expand, or then they try to row reduce 3 by 3 matrix, it turns out that the second spot in a 3 by 3 matrix will have the determinant of a 2 by 2 matrix in there somewhere. Kind of interesting. And then the slot, the third slot in your diagonal is going to be your determinant of 3 by 3 matrix. Correct. Correct. And also, if it's invertible and it follows all those invertible matrix theorems, A through R, all that's true. And now you can use it, yeah. Although we didn't really prove it, but you can still use it. All right. We could generalize to an n by n matrix by just expanding on a particular row where you cross it out, and then you'll have, if you have like a 4 by 4 matrix, and then you expand on the row, then your expansions will end up with 3 by 3 matrices, and then you can cross out rows, and then you'll expand to 2 by 2 matrices. So it all kind of is a recursive process that hopefully would be an easier thing to deal with. So let's see what else. I don't know. Maybe. So let's generalize. For a general matrix, n by n matrix, the determinant is going to be given by, again, here they're still expanding on the first row. Realistically, you can, another theorem will say that you can expand on any row or any column at that. So it's just going to be the element in that particular row or column that you're expanding on. In this case, it's the first row, times the determinant of whatever's left over matrix. And then the signs will alternate to a plus and minus, and it really depends on the position that you're in. Yeah, so this will turn out to be the row number and the column number. So your matrix, your generic matrix, has signs associated with them, and it really just alternates from a positive here and then whatever. So negative, positive, negative, negative, positive, negative, positive, positive, negative, positive. And so these signs will determine the signs of your determinant expansion. Okay? You have a question? No. When we do an example, hopefully this will lighten up a little bit. Seems really deep and theoretical. But it's only deep and theoretical because of the weird formulas that we're seeing here. Mm-hmm. 3 by 3. I don't know if there's anything really happening to it. It's just a process of counting every value, every number in the set. I don't know. Yeah, it turns out that you can pick whichever row or column. Should all be the same. So you do it one way, somebody else does it another way, and if you guys did it correctly, then your answer should be the same. So there's a couple of other definitions and theorems that the cofactor helps us. I don't really like the cofactor definition. The definition of the cofactor includes the positive and negative sign that's associated to the matrix. Why don't I just not do that and let's just do an example? Nothing. So let's find the determinant of this 5 by 5 matrix. Okay. So So what you want to do is that you can expand. So this theorem or this process over here expands on the first column, but I'll just make a note here. You can expand on any column or row. So that's what that last theorem said, where they introduced cofactors. Anyways, when you're expanding on any column or row, what you want to do is you want to pick as many zeros as possible. And so if I take a look at this, this has zeros, the last row. So for this particular example, I would most certainly be interested in expanding on the last row or last column. Oh yeah. Okay, well, I'm already at the row. This has a 1, so that has a slight advantage. Okay, so what's going to happen is that we'll assign the pluses and minuses. Let's figure out where the pluses and minuses are. Plus, minus, and plus. So it looks like I'm starting with a plus. I have plus 0 times, it doesn't really matter what this is, A1, 5. And then so if I go down with, if I start with a plus, the next one's going to have to be a minus. So the next one is 0 times another one that I don't care about. And here's the one that I care about because this one has a 1. So here you cross out the row and column in which that exists. And then you would take a look at the rest of the matrix that's left, which is a 6, 3, 2, 4, 9, 0, minus 4, 1, skip, and then 2, 0, 0, 0. Well, keep an eye on that, right? 4, 2, 3, 2. Oh, this should be a minus. Minus 0 plus 0. And star are those other matrices, submatrices that I'm not going to care about because it's going to get multiplied by 0. All right, so this is all I have left. So let's expand on, I would be interested in expanding on the third row here in this case. So this is equal to a bunch of zeros times, or plus 1 times this, the expansion of this. So I'm going to have a positive minus positive. So this starts with a positive again. Positive 2 times the expansion of the matrix that I get when I cross out the third row and first column. That's 3, 2, 4, 0, minus 4, 1, 2, 3, 2. And then I have a minus, but it's 0 plus 0 and then minus 0. Okay. So now you can expand on the second row or the first column. I think either I have 1, 0 left here, so that doesn't matter at this point. So I'll expand on the first column. So I have a 2, remember, that's still sitting there. And then so I'll expand on the first. I'll expand on the first row or first column, which has a minus 4, 1. This is a positive 3, right? 2 minus 0 times something that I don't care about, plus 2 times 2, 4, minus 4, 1. Let's get my minus 4 incorrectly here. Hopefully I did that right. Oh, I'm out of space. So we get 2 times 3, and then this one has minus 8, minus 3, minus 11. and then plus 2 times, and this one has a 2 minus negative 16, 18, and 33 plus 36, negative 33 plus 36. Is that 36? 18? Yeah. Positive 3 times 2 is 6. Yeah. So that should be your determinant. Should we check, or did you already check? I checked. Jessica already checked. So this is a determinant of A. Oh, if this is A. I don't know. Calculating seems so plug it in the computer kind of thing. Yeah. Yeah, if this one had been another non-1 number, then yeah, this whole thing would have been multiplied by that. Okay? That's how you find a determinant by hand. Of course, in the computer you say DET, and then you're done. And this is 6, which is not equal to 0, which means we don't know this yet, or we haven't shown this yet, or we're not going to show it. We haven't stated it yet as part of the theorem, but it means that this matrix is invertible. You can invert it. It also means the column spaces, row spaces, null spaces, and all the other stuff that we just learned. Okay, now imagine you have an upper triangular or a lower triangular matrix. Or if you even have a diagonal matrix, diagonal matrix. If you have an upper or lower triangular matrix, what's that going to look like? We have stuff on the diagonal, and then we have stuff here that may or may not be 0, and then you have stuff here that's equal to 0. Say this is an upper triangular matrix, let's call it U. And imagine expanding on this, right? So you would probably want to expand on the first row or the first column or the last row, right? Because there's a bunch of zeros there. So the determinant of U is going to equal to the first star. Let's call it star 1, 1. And then the submatrix that's going to be left after you cross that out, which is going to be the rest of the stars. The rest of the stars in the diagonal, and still going to be an upper triangular matrix. Plus or minus a bunch of zeros, right? So now you continue to expand on the first element, then you have star 1, 1, and then you expand on this new star, let's call it star 2, 2, that's the 2, 2 slot. And then you'll still have an upper triangular matrix with zeros in the bottom. And again, a bunch of zeros that come after. So you keep going through this process, and then you'll end up seeing that, well, the only thing that really seems to matter would be all the stuff in the diagonal. Yeah, so also the case for a diagonal matrix. So if you have a triangular matrix, upper, lower, or diagonal, then the determinant of that matrix is going to be just the product of the diagonal entries, which is going to be a really powerful theorem for us, because we've been row reducing all this time, and when we row reduce, we end up with usually an upper triangular matrix. So when we get that, then we can find determinants that way. So now what's left to do is, how are we going to compensate for those steps that we took to reduce? Yeah. Well, L, first of all, is unit L's, which means there's ones in the diagonal. So that's just one. So you're really just looking at U. Yeah. Yeah, maybe. Oh, yeah. Determinant's going to be 0. Yeah. Brian just made a good comment, interesting comment, that if you're reducing and then you end up with a free variable, that means your square matrix doesn't have the full set of rank, right? It means you have one free variable, you have at least one, your nullity is at least one dimension. And that means your rank is not the whole thing, which means it's not invertible, which means your determinant's equal to 0. So the questions in this explore the effect on elementary row operations on the determinant of the matrix. Let's take a look at all these problems over here. They look kind of interesting. All right, let's see what happens when we, oh, it's 2 o'clock. I just looked at the time down here. Well, time's up. I meant to give you guys a quiz over the weekend online, but I didn't. I forgot. So I'm gonna give you a quiz where you just have to download the quiz and then you have to do the quiz. It's on finding the inverse using step-by-step operations. You know the algorithm where you have the matrix A and then the identity matrix next to each other, and then row reduce, and then to get the thing. So I want to see the step-by-step process. No, I want what? I'll put it online for you. I'll put a PDF online for you to download. Probably on Friday or something, because it'll be online.